Both. Yeah, first, thanks, Lajos, for the great presentation. I enjoyed it very much, and you know why, because we're also working a little bit on that topic, although from a different perspective, but that was interesting. But today, I would like to talk to something completely different. The title is Wireless 100 Gigabits per second and Beyond, Technologies and System Concepts. And I would like to present a little bit more the hardware side of what we need to make those things work. So general consideration, and on the right side, you see the same picture Lajos already showed, but I will give a little different spin to it because, I mean, we both agree a high data rate requires large bandwidth, high SNR, and also multiple input, multiple output systems are an option. So millimeter wave or even terahertz frequencies offer those large bandwidth. And then we have this free space loss formula, which we all know. And if you look at the free space loss and also you look at the attenuation, the atmospheric attenuation, you can see that it is an important factor if you have long distance, but it's not really an important factor if you only have a short distance, as the application you see on the top right, some flash download in a manufacturing place or something like that. So if we talk about device-to-device communication or something like that, the atmospheric attenuation doesn't matter that much. But still, the free space loss increases with frequency, so we need high gain antennas and also in some applications, beam steering capability or something like that, if we do terahertz communication. So in 2013, we realized the first, at least we believe it was the first 100 gigabit per second wireless link. And as you can see, oh, my mouse, wait a second. I think now you can see the cursor quite well. You can see here what kind of technology that was. So here you had a waveguide part with a horn antenna, and there was actually a UTC photodiode there. So actually the signal was generated in the optical domain, and then it was converted by the photodiode, transmitted at around 240 gigahertz. And on the other side, there was a pure electronic receiver, an IQ mixer, and it was down converted. And the whole thing was done with arbitrary waveform generators and fast oscilloscopes and the software on those machines. And we were able to demonstrate the 100 gigabits per second in a combination of 3 channels. And you can see here it was 2 times 24 gigabit per second and 1 channel with 52 gigabit per second. This was a great result. It's a very highly cited paper, but at the end, it's just a technology demonstration, and the technology we used here wouldn't be whatever you can buy later, because this is just bulky, expensive waveguide-based parts. So the question I would like to raise, and I would like to offer a lot of examples, is are those technologies, are the required technologies really available? Because that waveguide stuff is great for building one part and shooting it to Mars, but it's not really suitable for making pieces you put in your cell phones or computers or whatever, where you don't want to pay thousands, 10,000s, 100,000s of euros for just one receiver or transmitter. So in my opinion, semiconductor technologies is not anymore the biggest bottleneck here, because we have silicon, germanium, indium phosphide, RF CMOS, and so on. We have those technologies which allow us to make highly integrated circuits, complete transceivers, even up to terahertz frequencies, and make them in mass production with high reliability and high yield. High-speed signal generation, this is something we can argue, and it depends on what we exactly need, but there was a big progress in the last years. So the hardware, DACs and ADCs, those things are there. The question is how power hungry they are and so on, but it's existing in the data processing. There's also a lot of progress made there. For me, the biggest bottleneck is the packaging and interconnect technology. So how do you put that in a package which you can do or realize in mass production to get those transceiver modules to work at terahertz frequencies? So what you see here is actually every dot is a paper. And actually in this paper down here, those guys actually, they looked at all those papers and collected the output power of terahertz semiconductors. And you see here the frequency, you see the power, And we can argue all the points, but here I only want to tell you one thing. I mean, it's just going down over frequency. So as higher we go, as less power we will be able to generate, which makes it even worse. Lajos already said that we have that we need more power at those terahertz frequencies to compensate the free space loss. But in addition, we don't even have that power available because those amplifiers go down, the efficiency goes down. So what we need to compensate that is a lot of antenna gain and even power combining to combine the power of several amplifiers to get enough output power of the device. How does high volume terahertz or millimeter wave packaging look right now? So on the left side, on the bottom, you see the picture, split block technology. That's how they place an IC here into a split block, which is a milled, it's a metal part, which is made on a milling machine. That's not possible for high volume. On the other hand, here you see the typical connectors we have at millimeter wave or terahertz. Coax up to 110. Now there is some coax up to 200, but it's very fragile. Here you have waveguide. Very interesting. I mean, that you don't even see the waveguide in the middle. You don't see the hole. So the flange is much bigger than the hole. So at the end, you have a transmission line, which is very thin, and you have a huge part around it. So in relative measures, the part is very big compared to the transmission line, and the losses scale actually with frequency. So that's also not very good. So the real big problem at millimeter wave for terahertz is always you have to bring your antenna super close to the amplifier, to the chip. So in automotive radar, they actually were able to improve regular PCB manufacturing to a quality that they can do 76 gigahertz antennas on a regular PCB, and even SMD soldered the chip on it. That's what you see on the top. On the bottom, you see a fully integrated radar transceiver at 120 gigahertz. The antennas are in the chip. So those things are now, this is available since a couple of years as products, and this is also now a product since a few years. So the basic problems you have is the interconnect between the antenna and the chip. And then if you go to PCB, the line spacing must fit the MMIC pad spacing. That's a problem at higher frequencies. And thick film technology anyway reaches its limits. So that 76 gigahertz stuff here is really kind of the limit what they do right now. So 100 gigahertz, in my opinion, is the limit right now for regular PCBs. Here's how I would like to classify or what we can find. There is split block technology, but that is only for space applications or other very expensive stuff. So what we are interested in this kind of surface mount technology, things we can do in mass production. And the biggest separation is antennas in package or antennas on chip. What I mean with on chip is on the silicon die, on the gallium arsenide die, whatever the technology is. Here is a lot of different ways to do it, and the biggest question is how to interconnect the antenna to the IC. So you can use wire bond, flip chip, and there is other technologies like embedded wafer level ball grid arrays, active mold packaging, and so on. I will show these things. So what we start now is with this part. First one is the wire bond interconnect. So there's always some pictures. I think everybody likes pictures. So here we actually realized an LTCC based package, and here you see the antennas, interconnect lines, and then there is some kind of cavity where the IC is placed, and then bond wires are used to connect the TX and RX signals, and then the whole thing is a whatever 10 by 10 millimeter big piece which can be soldered on a PCB, and the antennas are in here. Here you see from the side, so the heat goes back nicely off the chip, so you have an efficient heat dissipation. But the bond wires, they cause some parasitics. You have to compensate them, or you have to use lambda half wavelength bond wire or whatever, but that limits your bandwidth. So here we can see that 10% is doable, but not much more with this approach. The second approach I would like to show is using flip chip. Flip chip is great because those balls, they're much smaller than those bond wires. They are thicker. So the ratio between the conductor and the spacing in between is giving you a much better impedance. And the transmission line, if you actually assume the interconnect as a transmission line, is shorter. So that makes the interconnect much better. and it works for higher frequencies, but the problem is how to get the heat off. So if you flip the chip onto the PCB, it's very difficult to get the heat off the chip because you have to go through those balls. What we did here is we actually turned it around, so the MMIC was glued down as usual, the heat goes down here, and then the antenna was flipped onto the IC. Sounds like a perfect solution, and I still like it very much, but it also has issues like mechanically, thermally sensitive in terms of and there's this cavity because there's air below this antenna and things like that. There's also some things which have to be solved here, but you can get more bandwidth. So you see here it's 14%, but I'm very sure we can also get 20% out of this if we improve it further. Another option I talked about is this EWLB technology. I think I should have put a picture on how this works. Anyway, what they do is actually, if you turn this around, what they do is they take the MMIC, dice it out of the wafer, and then glue it the other way around on a wafer. So on top here is a wafer, you glue it down, and then you have some kind of a similar process as the end of the line process of a regular semiconductor process to make those interconnects. So it's a fan-out technology at the end. So what you do is you take those interconnects at the MMIC, fan it out to bigger balls to actually adjust the very thin pads, the very small pads on the MMIC to the much bigger transmission lines on the PCB. That was the idea. What has been done in addition, it has been used to put some antennas in here. So what you do is you actually use the ground on the PCB as the ground of the antenna, and then you have some super straight style antenna here. What you see here is an antenna at 140 gigahertz, which works nicely. Here you see the impedance, have a bandwidth of 14%. So this is also a good thing because it's an existing technology. It's a process you can use, but it has a lot of limitations because you can't just adjust the spacing as you want. You always have this mold material, which is not super great. And also there is also some heat issue because the heat has to go down through those balls and there is limitations there. Another thing which is very new, which is, I think this was last year or something like that, 2 years ago. There's it's active mold packaging. So they use the regular molding technology and then they activate the surface only where the gold should go, and then you can put this antenna on top of the mold itself. Here you see some kind of bow tie slot antenna, which also has a bandwidth of 14%, and then there should be through mold vias which connect the signal to the signals from the chip. So it's a little similar to EWLB, but it's a completely different manufacturing process. But it also has similar pros and cons. Last one I want to show is silicon micromachining. That is actually a process where deep etching is used to process silicon. Can be done very, very accurate. Afterwards, the silicon is metallized, and then you can stack a lot of silicon layers, and you can have 3D structures, even put waveguides in it, and so forth. That has been shown for very high frequencies, up to the really to a terahertz and above. And but at the end, the remaining issue is still how to connect the active device, the silicon, indium phosphide, whatever. And here you can see in this paper they have shown that they have done it with the bond wires. So it has the same limitation. It's a super great technology to do passive devices like filters, antennas, and everything. But the limitation factor, in my opinion, is the interconnect. So with this, I would like to switch to the on-chip antennas. When you think about on-chip antennas, you first have to look how a chip looks like. So below there is silicon. The silicon has, for example, 700 micrometer thickness. That's a typical wafer. And then on top, you have just 15 microns where the whole music is playing. So there is the transistor down here, and then there is those metal layers they're using to route the signals on the chip. And those top two metal layers, they're usually used for RF signals because they have a certain thickness. But this layer has only a spacing of a little bit more than 10 microns from this layer. So if you want to do a real regular PCB style antenna, the substrate is so thin that you don't get efficiency and bandwidth at the same time. It's very difficult to make an antenna there. The other option is you don't put ground there, but then you will radiate into the silicon. And the silicon is a very high decay material. It has an epsilon of 11.7, and that means you are generating mostly a substrate wave. And especially if your antenna is at the edge between air and silicon, and those 15 microns don't play a big role, there's a formula from this paper here, and you can calculate for silicon, 96% of the energy go in the silicon. So that's a problem. One way out of this is to just make use of it. Okay, let's use the 96%. How do we do that? If we just do it like that on the left, we will mainly have substrate waves because we have reflections here and back and forth. So it's gonna, the wave is mostly going to the left and the right. So it's transmitted in the substrate. One way to get out of this is just to put a lens on there. And the important thing is that lens has to be the same epsilon or very close epsilon to the silicon, because then there is no refraction here and the signal goes in the lens, and then it would work without the matching layer, but then you get a big ripple over frequency. If you put a matching layer there, quarter wavelength thick, and the epsilon of the matching layer is the square root of 12 or 11.9 in this case, then you can have a nice performance here. So that's one concept a lot of people use. So we've done this here. If you think it through, you will realize there's one remaining problem, because I have to take that silicon lens, I have to mount the chip on it. Below the chip, I have to keep air, because otherwise this interface and the 96% thing doesn't work. And then how do I get the signals from the IC? How do I get the heat from the IC? So that is a remaining problem. Here it worked because that was just a radar IC actually, which had a very low power consumption. But for communication ICs, it's going to be difficult to get the heat off. And in addition, this cavity is also some tricky things. So those are the cons here. But you can see here, it's a funny device. So on this side, it's an SMD solderable device. On the other side, there is this lens. So you take the thing and solder it on a PCB, and you're done. Another option, what people do is they actually try to do this PCB style antenna in the back end of the line of the chip, and then use some additional elements to actually, let's say, suck the energy out of the device, out of the PCB style antenna, which could be a dielectric resonator like shown here, or it could be a parasitic patch like shown here. So for the dielectric resonator, I've shown some results here which come from that paper. I mean, the issues are clear. It works quite okay. It's not super broadband, but if you can live with this kind of bandwidth, it works nice and it's very compact. But I mean, everybody can see what the problem is. Very high requirements in positioning accuracy and a dimension accuracy. Another thing which came up recently is this, and I'm always showing the papers here where I'm having this from. Not everything is from our group. What they've done here is they just take the silicon away. I mean, we discussed the silicon is the problem, so why not taking the silicon away? And there is actually a process which is called localized backside etching. So they take the silicon away on the back. So they really take it completely away. So you have a little membrane here, which is 15 microns thick, that's all. And the interesting thing is, for our transistors, we don't need all that silicon. They still work. It's a mechanical thing at the end. I mean, this is very fragile, this part. Second, if you glue that chip somewhere, you have to make sure that the whole thing down there is not filled with glue. So there's practical issues which have been solved, and it requires an additional process step, which is not that simple, but otherwise it works quite nicely. I don't have results pictures here, but they're from the publication. So you can see again, a quite good performance at this in this case. One last thing I would like to mention is, I showed that before, is power combining, because we've shown all those examples, but an additional problem we always have is power combining. And most people, what they do is actually they take lots of amplifiers, they have a combiner, and then they hook it up to the antenna. That's one thing. Then a couple of years ago, I saw a few papers and they were titled with free space power combining. and they were talking about a new idea like free space power combining. So what they do is they take amplifiers with antennas and combine the power in air. I hope you see the same thing I see. For me, that's a phased array. And it's not really new. But it works, I have to agree. But there's two things it can't do. First, the radiation has a smaller beam. And second, you cannot combine this kind of thing with a lens. That is obvious, because then you get a broader beam than you want. If you want to use a lens, you have to have your power radiated from one phase center, from one center. So one additional thing we came up with is, why don't we combine the power in the antenna and just save the power combiner? Just don't even need it because we combine it there. I mean, one simple thing everybody does is differential fed antennas. That is already combining two amplifiers, a differential output of an amplifier. So this is a typical differential antenna. There's different shapes, but it's a slot antenna which has two connections, 0 and 180 degrees. So you can have double the output power compared to a regular amplifier. Why not using 4 of those things? Depending on how we put the phases, we can either have 2 different channels, or we can combine them in a linear polarization, or even do circular. If we do circular, we could even add more of those slots. And what we found is there's actually this picture is from a paper down here. He analyzed lots of different power combiners and what the efficiency is, because if you have power combiners and you have more and more, at some point the additional power you gain is eaten up by the losses in all the transmission lines, and that's why this thing in reality goes down again if you add more and more power amplifiers. And here you see the range between transmission line concepts, couplers, T-junctions. Blue is ideal if you have no losses, and then red is actually what we found from all these experiments we did with in-antenna power combining. Here you see examples. What we did is on the left side, you see that we used 8 slots, and the signal is actually fed in here. The signal goes in a ring, and here you see the signal is going out into an amplifier and then back into the antenna. Same thing for all of them. And due to the ring, actually the phase is going 45 degrees different from each of the feed points. Obviously, you have to make sure that the right amount of power is going to those amplifiers to have the same amount of power at all of those 8 antenna feeding points. And then here is the chip. That's a photo of the chip as we measured it. And here is the performance. We don't have to discuss the numbers itself, but what you can see it is that when, oh, still the German, okay, sorry, but I think it's easy to translate in English. So it's when you have the active antenna with the amplifiers, you see there is a limited bandwidth. So the bandwidth in this case is more limited by the amplifiers than by the antenna itself. Here you see a case of a linear polarization, and what you can see here, we even have 2 feed points at one of those antenna, single antennas. So there's actually 8 feed points as well, but there's only 2 crossed slot antennas. That works as well. And we have shown a bandwidth which going, actually we measured from 200 to 260 here, but we have other measurements with even more bandwidth. So this thing can support over 100 gigahertz of bandwidth at this kind of frequency range. This thing was actually a complete communication transmitter. So we built it in this device here and did transmission measurements at 200 gigahertz. Yeah, with this, I would like to close the talk. I think I've shown you a lot of different packaging solutions, some from my group, some from others, to just give you all the range of what is researched right now. And I think with all those solutions, we will be able to actually fill the missing point, which is the packaging technology, to make those things really become a low-cost devices we can use for communication and also sensing in the terahertz range. And one thing you can keep in mind is that depending on the frequency range and the antenna size requirement, SMD technology with patch antennas, that's for the low millimeter wave range. If you go higher, you will have fully integrated SMD system in package solutions using off-chip or on-chip antennas. And as higher the frequency goes, as more we tend to on-chip antennas. So I would say 300 gigahertz is kind of the point where we would probably have mostly on-chip antennas, and below rather also use off-chip antennas. Yeah, with this, I would like to close the talk, and I'm expecting your questions. I hope I didn't take too much time because the clock disappeared during my talk.